Um, so everybody, thank you for joining this morning and evening for us here in North America. But today we want to talk about the route-based monitoring, right? And kind of ask the question: Is this becoming obsolete today? And it's quite a weight topic, I would say. But I'm sure that the end conclusion will all help us in the good direction. So we're going to at first look at a brief history of the route-based monitoring to understand why we are today where we are, and point out what some of the limitations are today of the handheld data collection process, right? And why there is kind of a plateau that we reached. Then we will point out some of the key advantages and disadvantages of the route-based monitoring versus potentially some wireless permanent installed sensors, as well as go over calculation example of how maybe to compare the return on investment, right, for both approaches. Further, we will review what are the key considerations to keep in mind when comparing vibration data from different sources, and try to create some context around like what difference is actually relevant, right, and why, and how to properly value that difference. And at the end, we'll highlight a couple important factors on the IoT technology today, right, and how it can help accelerate our maintenance 4.0 strategy. So I would say let's get started here. And as Stanley mentioned, if you guys have any questions or concerns, there's a Q&A option there. We'll try to answer as much as possible.
Dice, can you be a little louder? I guess the voice is not clear. Okay. Thank you.
Yeah, I think Mr. Bijendra, I think you need to increase your volume because the volume is very clear to me. So Trace, please go ahead. Yeah.
Okay, thank you. Yeah, if there's anything else, please don't hesitate to interrupt me. Okay, so let's look at that the history of the route-based monitoring, right? And basically, as you can see here, right, if looking at that history of route-based monitoring and more exactly at the evolution of the data collection hardware, right, you see that we came quite a long way. And when we saw the first digital data collectors were very limited in capabilities due to the memory restrictions, right, and the cost of the very early AD converters and actual signal processing hardware. And so these initial tools were very extremely expensive and then really only found for troubleshooting on some of the most critical pieces of equipment, right? I would talk about gas turbines and other multi-million-dollar equipment where they first started using these vibration analyzers, right? At that time, software was unheard of and all data was reviewed manually. And often actually the plots were printed out by the device itself, right? As the data collection hardware and processing hardware became developed further, and then the costs starting to go down, we saw the introduction of more user-friendly, let's say, tools that could actually adjust sampling rates. We could change the different filter settings and do even some integration of the actual signal, right? So we started really getting a more usable tool, right? And then as that was developing, also, of course, the personal computer was developing, and then we start seeing the first software that actually was compatible with the device. So we can start creating some topology of assets, right? The machine tree, which would then allow for that historical data storage and comparing, as well as some of the route functionality. And over the years, I mean, obviously the devices kept getting better, right? And technology kept developing. You see today we have almost no more memory restrictions, right? As you can now have easily a 50 gigabyte little SD card, for example. So memory is really not a limitation anymore. We have multi-channel 24-bit AD converter devices, with even some fancy tools like automated measurement point recognition through RFID, for example. And so basically, as we developed from this very first data processing tools to what we see today, we came quite a long way. But in the last couple of years, there's really been no significant improvements apart from small little steps, right? So it seems we kind of hit a plateau basically on the hardware and how it has developed. And the main driver behind that is really that the hardware is really not our limiting factor anymore. And so if we look at the modern route-based programs, and they require very highly skilled and trained analysts, right? To if we look at what that analyst, what does it entail to take these route-based measurements, it's basically we need to collect and analyze the data and then create reports on the findings. And that's where we spend roughly 80% of our effort, right? In collecting, analyzing that data, and then creating some way of communicating our findings. And then the second part of the analyst's job today is defining the actual maintenance actions and then following up on them, as well as troubleshooting the machines that most benefit from the attention and to troubleshoot some of those machines. That only takes maybe roughly 20% of the analyst's time, right? So there's kind of a discrepancy here saying, hey, and we have this 80-20 rule between, the Pareto example saying, hey, 80% of my results come from 20% of my effort, right? And that's kind of exactly what happens here, right? An analyst spends 80% of his effort in the collecting data, analyzing them, coming up with findings and trying to communicate them. And 80% of the value is actually in the latter part saying, hey, with that advice, what are we going to do now? What maintenance action should we take? Do we need to follow up on that? Do we need to create additional, take additional data, troubleshooting measurements, maybe for some root cause analysis? So that's really where the biggest limitation is, that we spend most of our effort on that data collection, and most of the results and most of the value is actually created in the latter part here. But most analysts simply don't get the time for that, right? And this kind of shows where the biggest improvement is right now, not on that data hardware, but on this restoring this balance between the value creating tasks. If we look further and then kind of zoom into some of these limitations of the route-based monitoring, then we see again, right, that what we talked about, those resources, and we require really high-skilled personnel to collect and analyze that data. And it's seen that an analyst typically spends more than 2/3 of the time to actually collect the data, right? And making sure they have good data, and only 1/3 of the time and then doing the analysis, plus coming up with findings and some of the additional tasks that they're talking about, right? And again, here you see that effort versus result, that Pareto 80-20 rule is really applicable here. And the question there is, hey, is there not a better use of my highly qualified personnel than just collecting that data? And then further, obviously, there are some limitations on the scheduling side, because equipment needs to be running under stable process conditions, and it can be extremely challenging for equipment that runs in batch or an intermediate process. And sometimes there's a need for special planned maintenance window for data collection, right? Because there is no stable time to actually measure it. And now if we're having to plan a maintenance window to actually collect the data, that kind of beats the purpose of avoiding downtime, right? At least this is planned downtime, but still it's something we're trying to avoid. And then, of course, more and more important is the safety aspect, right? A lot of times we need to install remote sensors because we cannot safely access a specific machine while it's running. So we need to wire those sensors to an accessible location, to a junction box. And that's obviously quite a significant cost, right? Now you're installing permanent sensors just to collect the data on a route-based interval. And then, of course, resources available, right? We have our trained analyst, but this person is very wanted throughout the company because he's very knowledgeable on the machines and on the potential problems that there are. So a lot of times it's hard to stick to the schedule, right? because their time and energy goes to the problem machines that actually need it, right? Because that's kind of the nature of the human trying to go where they add the most value, right? So it's hard to stay on top of the just data collection. Further, we have a couple more important limitations are really like the repeatability, right? How is that delayed data collected every time? And from measurement location to the actual process conditions during the measurements, and the engineer collecting the data needs to ensure that the data quality is of high and that it creates value to the program, right? Because else there's really no point in collecting the data if you cannot even use it to draw conclusions. And then of course that measurement frequency, right? You can only collect as often as we can schedule it, which is often happens at a monthly, maybe a quarterly, even a yearly intervals, taking that data. And the question is really what happens in between those data shots, right? We don't know. And in the graph shown below here, it's an example of a wireless sensor graph, plus then the blue line kind of indicates your monthly measurements. And monthly is actually quite often, right? A lot of times it's done much less often. So consider here, every month we take measurements and everything is stable, slight increase until, and the last two measurements potentially triggering some kind of very early change, but nothing really drastic. And then suddenly this thing basically just trends up, and the next measurement that you would take here would really be, the machine would probably not be running so good anymore, right? So what we're really trying to show is like, hey, there was an anomaly event here, kind of an early warning. Plus then you see that increasing trend more clearly, and that sudden increase, right? In that last month period, we saw a steep climb. What really, that fault really started developing. And we see this quite often, right? This is one example, but you see quite often that certain fault modes develop fairly quickly. So the question is really like, hey, if we only measure this monthly, we would really miss this fault quite significantly. And that's really another limitation, saying, hey, what are we really missing by not measuring very often? Further down, I'm looking a bit more to comparing some of these parameters of the wireless system versus a route-based system. To kind of say, hey, I call this, we're kind of already segued into this topic, which is the elephant in the room in a lot of predictive maintenance ops today, is like, hey, how can this wireless technology that's emerging so fast, how does it compare to my route-based monitoring, and how should I compare the two, right? What should I need to keep in mind to compare the two? So if we go further there, and we put the route-based and the wireless monitoring side by side and evaluate the couple of key features, right? We can see here both technologies find their best use with the goal to extend measurement interval as much as possible, right? And the handheld data collection has a heavy focus on early detection, right? Because the earlier we can detect the fault, the less often we have to measure, which obviously helps us quite tremendously. But with that very early data collection, with that very early fault detection, we need to have very high quality data, and we need to have very high quality data and also high frequency, right? Because that's where a lot of those early faults will first show up, is in that high frequency range. So that's obviously on the handheld side very important. Now, if we look at wireless, and now we start measuring every minute or maybe every, let's say every hour in certain cases, we have so much more data that it becomes much easier to detect these anomalies, right? And detect changes in the condition of machine. And that's really what we're trying to do. Instead of detecting very early, we're just trying to detect early, but we're monitoring continuously, so it's much easier. And then basically repeatability becomes much more important than actual, that accuracy component, right? Because we have the algorithms that are basically going to look for that repeatability and look for changes for us. So that's a big, that's kind of how the two different technologies can be looked at. And of course, and measurement locations can be inconsistent, right, with a handheld device, and repeatability is a lot of times an issue. And with a permanent installed sensor, there is no question, right, if the sensor was moved or it was measured maybe on a different machine. So that's really not a problem at all with wireless sensors. Additionally, having your knowledgeable and hopeful, passionate vibration engineer on site to collect data allows for that first-hand experience of the machine behavior, right? Where hear, feel, and smell is a lot of times what these vibration people say when they're actually in the field and trying to understand what machines are doing. And this obviously is very is challenging with a wireless sensor. But what we do these days is basically integrate technology, right? Vibration, acoustic, temperature, which is kind of is your hear, feel, and smell, to bring that into trendable data, right? Because the downside of your analyst being in the field, you're not able to trend that, right? That's his knowledge, his experience that tells him, hey, something's wrong with this machine. On the other hand, if you now start measuring and trending these parameters, and basically they become useful data points that you can actually draw decisions of, right? And have algorithms to then say, hey, there is a change in the sound of this machine, instead of the vibration analyst having to use its experience to do it. And then, as you see, this on-site observations are a benefit of the handheld device. But then with a wireless system, you don't need to physically go to the location, right? So a lot of times there's remote locations or very hard to access. And potentially with cellular technology now integrated in the sensors, it becomes very easy and very effortless to actually install sensors, right? You literally install the sensor, turn it on, and it starts communicating just like yourself. And then, as I mentioned, acoustic, temperature, and vibration will help you in actually getting that hear, feel, and smell of the machine and making it trendable data. And so kind of looking at those different factors at play and considering today's available technology, for most applications, wireless permanent sensors are a great way to actually continuously monitor an asset over the lifetime of the machine. And then we use the handheld tool for the troubleshooting together with that experience of that engineer to allow for troubleshooting the problem and kind of the deep dive behind it, right? After you detect a specific fault mode, potentially with a wireless system, you can then go do a root cause analysis with your actual handheld device. And so that's kind of, if you sum these things up, what kind of the natural conclusion comes out of that. And further, of course, this is more like from a features perspective, but also money-wise, right? The ROI and the return on investment is important. And the only proper way to really compare these types of systems is by looking at creating some kind of probability of avoiding downtime, right? Avoiding that unplanned downtime. So if you look here, there's different levels of automation, right? From zero automation here with the manual data collection and analysis to like fully automated systems, right? Where we detect anomalies, we then identify the specific fault mode, and then we define a remaining useful life, right? Out of from a wireless sensor show automatically done. So the probability of avoiding that downtime is basically from 0.3 to almost 95%, right? So 30% of avoiding downtime with everything done manually, and then different levels of automation and maybe wireless sensors, but no automated anomaly detection. You go up to 40% because now you have more data, so it's easier to find changes. And then going further with anomaly detection plus certain characteristics, and then you kind of come to the perfect, the most advanced system today is like that 95% probability of actually avoiding any downtime. And so that's kind of what probability you should use when you're trying to compare these return on investment, saying, hey, if I invest X amount of money for my handheld data collection, I got a chance of 33% to avoid unplanned downtime. If I invest maybe more money in a more advanced solution, well, my chances of success, my probability of reducing downtime actually increase. So your return on investment will increase as well, right? So if we look here for a basic example of 40 semi-critical machines, right? And for each of them, we can avoid maybe 4 hours of downtime per year. And let's say it costs $4,000, right, for this machine to be down. So that would potentially is a total of $640,000 per year of downtime if we don't do anything. Now, we look at a manual data collection every month, right? So quite often, we say, okay, the hardware costs us maybe $25,000 plus the software. We spend $12,000 for the engineer to actually collect the data, evaluate the data, and draw conclusions out of it. Then we correct our downtime with that number, right? Because there is only 33% chance that we reduce downtime. So basically, there's still 66% probability of that $640,000 total downtime. So we come to that $422,000. So your total cost is adding those all up. It says $460,000, which basically gives us a return on our investment at the first two, or our investment here of 1.4, let's say 1.5 times my investment, which is good, right? You're still benefiting from your investment. Now taking the complete opposite, right? The most advanced system at the bottom one here on our automation scale, we come to a system that's wireless sensors with fully automated analysis. Let's say we pay $72,000 for 160 sensors. Now our downtime is reduced, and the probability of downtime is now only 5% of that $640,000. So we come to $32,000. And as you see here, that brings us to a total of $100,000, right? If we're correct for that, which gives us that ROI of 6, right? So that the dollars you spend here earn themselves back quite a lot more, and this making it really that these numbers really speak for themselves, right? With a higher initial investment, and maybe you spend $50,000 more, 50% more initially, you get an ROI increase of almost 4x, right? Which is something management people are really looking for, right? And say, hey, this is what makes sense, and this is where my dollar the dollar I invest will basically earn the most. So that's the financial side of it, right? Which is also very important when we're trying to bring this up to management. Now, going a bit further into this, there's also after looking at the ROI, return on investment, very important, but technology, right? And once we're having these technologies in place, the question is, how do we compare them, right? And there's we start looking into the purely technical specifications. By putting the different technologies side by side, we will understand that the strengths and limitations are of each, and this will help us make an informed decision when comparing them. And we will discuss the different sensor types, measurement hardware, and then internal and external factors that we should consider and when we're trying to actually compare these different systems, maybe data from a handheld device versus data from a wireless sensor. And these different aspects are important. And then at the end, we'll kind of talk about what difference is actually important, right? Put in perspective what X amount of difference actually means. So going further here, and you see we have different hardwares, right? We have obviously the proximity probe, eddy current principle. You measure relative motion between your housing, the bearing housing typically, and the actual shaft. And it gets very expensive, right, to retrofit this. Then we have the seismic bolometer with an output of millimeters per second or inch per second. This is a magnet in coil, right? So literally a moving piece inside of there. We don't need an external power supply, and these things are very temperature sensitive, right? And then as we develop further, we see the most common today is that IEPE sensor at the piezoelectric, typically an accelerometer, also available in bolometer, through integration built in. Some advantages: high temperature, high F max, right, up to 20 kilohertz or higher these days, but not such a great F min or low frequency. Then the fourth one here is our MEMS which is a microelectrical mechanical system, as you can see here, right? It's typically capacitive or piezoresistive, and very low power consumption, right? That's why this is the prime candidate for wireless sensors. From DC, so from 0 hertz up to, at these days, 8-10 kilohertz. Very small footprint, so very small sensor at a very low cost. So again, that's why it's a prime candidate for wireless sensors. And then the biggest limitation, probably from a vibration perspective, is potentially that reduced Fmax, right? Like 8, 6, 8, 10 kilohertz, depending on which sensor you're looking at, can be sometimes limited for certain applications. And the fifth one I put in here is the force detection sensor, which is actually based on the strain gauge principle. It will actually measure the force or the strength, the torque inside of a housing, and out of that basically measure the dynamic force plus the static force, which will give you an indication of the movement in the shaft, right? So it's very easy to install, and it's special applications, right, for sleeve bearings, crankshafts. So that's another sensor that we see once in a while, and it's good to know that all these different ones exist. If we go to kind of like looking at different factors of the piezoelectric, right, the ICP sensor as it's commonly known, and then the piezoresistive and the capacitive, which are the MEMS sensors, and then different aspects, right, and the more points they have, and the further out the color goes, indicating, hey, that's the sensor does very good there, right? So you see the ICP sensor in blue here, kind of masked by most of the MEMS technology today, but better bandwidth, as we mentioned, higher G, right? So that maximum measurement that it can take is higher, which can be helpful, and it's a very robust design. Now, if we look in the MEMS, the yellow and the pink here, or the kind of pinkish, you see that basically they cover a lot of different bases, right? And actually, thanks to these recent developments in the last couple of years, now we have much lower noise than we used to, and we'll talk about that more. We get a higher range, frequency range, and so there's really some advantages of the MEMS in the last couple of years that bypass the downsides. And further down, right, if you look at a sensor, what specifications are important? First of all, obviously frequency range, right? We're trying to compare maybe two different measurements. So the question is, hey, what frequency range did I have here in my sensor? Which one did I have here, right? Each sensor technology has a different frequency range, and basically we mean the usable range, the linear range, which is typically that plus minus 3 dB, right? Where our accuracy goes too far away. So it's important to know that we should only compare data inside of that frequency range. And then the sensor noise, often with MEMS, it gets mentioned, oh, noise, they're very noisy sensors. And so that noise is an important factor. Sensor noise defines the actual minimum resolution, how small of a signal you can measure. And it basically influences low frequencies, because if you integrate your signal, you get that little low frequency noise gets exaggerated, and low amplitudes, right? Obviously, if you have very, very low signal to noise ratio, then that will influence that as well. But kind of comparing, let's say, the influence of noise on a signal, I took a low cost accelerometer, ICP sensor, right, the piezo sensor, and a standard MEMS sensor. And comparing the noise density, you see 2.3 mu G and let's say 700 mu G. So you think, oh, wow, that's really a big difference. Like, no way this MEMS sensor is going to be any good. But if we look at the actual influence on our signal, you see at a 1 G peak at 10 hertz, a piezo will give you potentially 0.0114% error. And that's MEMS sensor with these noise settings will potentially give you 0.07% error, right? So basically 2 times almost nothing, right? Especially considering that most sensors have a plus minus 10% accuracy. So then this noise influence is really close to nothing. And then further, if we now say, hey, we look at an overall value, which obviously we're, instead of one frequency amplitude, we look at a calculated overall value. So the RMS acceleration from noise in a 0.1 kilohertz overall value, right? So we're going to see for that MEMS sensor with 700 μg, that actually would result in 0.022 G worth of noise, right? And if we look at that piezo sensor with the 3 μg, it basically comes down to 0.00094 G, right? So very little noise, but then look at that MEMS, like 0.02 G is really not something we're concerned about in the vibration world, right? So that MEMS, the high noise on the MEMS is really becomes irrelevant when we're actually measuring some meaningful vibration data, and influence is basically neglectable very easily. And keep in mind, MEMS versus a piezo. If you have MEMS in a wireless sensor versus a piezo with a handheld device, there's almost 100x price difference, right? So that's what you're comparing here, and the error is really not significant to worry about. Okay, what else is important, right? Obviously, different ways of collecting the data. We have handheld data collection with a handheld device. Periodically walk around, typically using a magnet mount or permanent installed sensors. And then you go with that device to your computer and you upload the data to the software. We have wired online systems, as you can see here, right? Permanently installed sensors to a unit that will process the data potentially continuously or on a route basis. And then the data goes automatically to the software. And the last year, wireless online monitoring, where we have permanent installed wireless sensors, and then a wireless gateway or cellular sensors directly to typically a cloud where the software resides, right? And so the three different ways of getting the data from that sensor to some software for evaluation. And then what's important from an external consideration is and what can influence the data externally, not the sensor, not the measurement device, but externally, it's obviously the time of measurement, right? If I measure now and I measure maybe 5 minutes later or an hour later, this machine can be doing something completely different, right? The process can change very significantly. So therefore, it becomes very hard to actually compare that data, right? We need to keep in mind, hey, what happened with that machine if I'm trying to compare one measurement with another measurement, saying, hey, I need to make sure my process conditions were the same. And the only way to guarantee is to measure at exactly the same timestamp. And then, of course, environmental changes. Potentially, there's a nearby machine that is inducing vibration or anything else like that. So that's something that can also not be excluded when you don't have data exactly the same timestamp. Mounting method, another important factor to consider is if you use a sting probe, as we call it, or a two-pole magnet, flat magnet, adhesive, you see that the linearity basically of your signal changes quite a bit. So you can have a sensor that goes up to 10 kilohertz or 20 kilohertz. But if you install that sensor with a two-pole magnet, now your useful signal is only up to maybe 6-7 kilohertz, right? So again, at that mounting method, if you're trying to compare data, keep in mind what part of the data is reliable and not influenced by this potential, is inside of the linear range of that mounting method as well, not only the sensor. And then additionally here, at that mounting location, I think that's one that gets very often forgotten. If we talk triax versus signal axis, right? So you see here two sensors installed on the same bearing. And then you can imagine if I measure my horizontal vibration on the side of the bearing housing, and I measure that same horizontal vibration on the top, it's purely geometrics, right? That the movement up here will be maybe twice as large as the vibration up here, because at the end of the day, we're measuring movement. The vibration up here will be twice as large as the vibration measured down here, right? So if we're trying to compare data and trying to make any use of different systems, it's important to understand where was the measurement taken. And the only proper way to compare is, again, exactly the same location or right adjacent to it, right? because you see this little geometric graph that I like a lot, gets forgotten quite often. Further, looking now we have the data collected. Looking at the internal factors that we need to consider is the measurement settings, first of all. Frequency range, right? As you can see here, we're calculating an overall value, maybe from 0 from 10 to 1,000 hertz, or from 10 to maybe 8,000 hertz. So it's really important that your overall value is, if you want to compare it, make sure it's from the same frequency range, right? Because else there's really no point. Now you can imagine that this overall, the second overall value will be much bigger than the first one. Other things important when looking at measurement settings is averaging, right? How many averages were taken, and that can influence the signal, especially if you have impact type events. And then the window function, right? Depending on the type of window, it can. So certain windows are very good in frequency accuracy. Some windows are very good in amplitude accuracy, but it can make quite a big difference on your actual signal. And then once we have the data in our software, obviously the unit, right, acceleration, velocity, displacement kind of speaks for itself. Acceleration is good at the high frequency, representing the high frequency data. Displacement, low frequency data, and velocity is kind of a flat line when it comes to the amplitude response, but only up to, let's say, 2-3 kilohertz, right? So that's kind of an obvious one. Obviously, you should compare the same unit. The next one gets quite often we forget, and is the statistical parameter. So RMS, zero peak, peak to peak, crest, kurtosis. How are we displaying this data? And I give a good example here, saying, hey, I have a signal here, zero peak, peak to peak, RMS, right? A nice sinus wave. So my RMS is multiplied by 1.4 is going to give my zero peak, only valid for a sinus wave. If I go to the right-hand side here, I have a very impact-like signal that dampens out. Well, my zero peak and my peak to peak are basically exactly the same as this nice sinus wave. But my RMS value is almost nothing, right? Because the energy in that vibration is negligible. And so therefore, again, if you're comparing RMS or zero peak, very important. And don't make the mistake to just use the 1.4 conversion, right, from zero to peak to RMS, because if you're talking about an overall value, a complex vibration signal, that does not hold up, right? That rule only counts for a sine wave-like signal. And then what difference really matters, and this is one of the last things here, is like, hey, I have, let's say, a difference of 0.5 millimeters per second, right, at 0.02 inch per second. What does that mean, right? I look at a signal of 0.2 millimeters per second versus a signal of 0.7 millimeters per second. Well, now I have a 350% error, which is unacceptable, right? Everybody's going to be like, whoa, that is ridiculous. Well, how can I have so much error? Now, putting this in perspective, let's use the ISO, right? ISO 10816, saying, hey, we have this machine maybe falls into the group 1 flexible. So I would only be concerned about vibration on this machine if it reaches more than 4.5 millimeters per second. So let's say something reads 4.5 millimeters per second, another sensor gives me 5 millimeters per second. That same 0.5 millimeter per second difference, but now it's only a 10% or 11% error, right? As you can see. So really putting that number in perspective is very important, because 10% error is very much acceptable versus 350% error. Nobody wants that, right? But you have to keep in mind that most actual sensors have a 10% margin regardless, right? So that the 11% error here is really negligible. And that's really the proper way to compare it. Like if I have 0.5 millimeter per second difference, okay, what is the maximum vibration level I'm concerned about, or at what level would I be concerned? And then we can use that as the benchmark, right? And go from there. And also today with analysis capabilities, nobody really looks at these fixed thresholds apart from maybe for acceptance testing, right? That's where something like an ISO can come into place. But in reality, we adjust our thresholds to the actual machine condition, right? And our goal is to detect changes over time. So repeatability is much more important than accuracy at that point in time, right? And then obviously with technologies like machine learning and algorithms or artificial intelligence today, typically you have a learning period in which the algorithms will review the data and basically learn how the machine behaves, and then generate certain threshold levels. Say, okay, this is how that machine runs in a good condition, based on overall values, based on specific fault mode trends. And then from then on, you have an AI-powered monitoring, right? Based on the actual machine condition, and if that changes over time, the algorithms will automatically flag those anomalies and potentially identify a fault mode and calculate remaining useful life, right? So that, again, jumping back to here, that 0.5 millimeter per second we started with was really not that critical. And then here, one of the last slides, how can my IoT program actually accelerate my maintenance 4.0 strategy? And just a couple of things I like to put in your head, because I think that's really where the value is, that we can, with IoT, in industrial Internet of Things, we connect systems, right? And that's really the value, because these connected systems give you the full picture of data, right? We have process data, we have condition monitoring data, and the combination of those two is really where the value is at. And that both those pieces of data can go to our process control, they can directly link insights to a CMMS system, for example. So connecting these systems is really where the value of IoT comes in. And then, of course, the analytic and machine learning power, right, where we go from pure data to actionable insights, right? Instead of having a system that provides data to us and we go and figure it out, now we have systems that provide us insights, and they can tell us, hey, this is what you should look at. And that's really where most value is created by this maintenance 4.0 changes that we're seeing right now. And then the key takeaways here at the end is really, because I'm taking a bit too much time, your handheld data collector development, right? The hardware is about as good as it's needed today, and we kind of reached that plateau. And the main limitation is that skilled personnel, right, to collect that data, and only 20% of their effort creates 80% of the value. So the biggest improvement we can do is kind of tip that scale, right? Having them do more value creating work by automating the data analysis, anomaly detection, and fault mode identification. By having systems do that for us, now this vibration analyst can focus his skills on actually the problem machines, the machines that need it, right? So there will always be a place for both technologies, right? For wireless sensors to automate that data collection and create insights, insightful data, and the skilled personnel to use their handheld device and their knowledge to help with those problem machines. And then we went over all the important factors to consider when you're trying to compare data. Maintenance 4.0, the connected systems that you provides you that full picture, and then the analytics and the machine learning that will help us create those insights in the data. And that's really, I think, the main things that I wanted here today to get across, and I hope I was able to do that. So I'll switch over to Tanmay again and kind of see if there is